Hi, this is Sam Welker with ThinkParticle.com, and in this video, we're going to be talking about the TP Toolkit. This is part of the visual documentation series, and in this video, we're talking about the TP Dynamics object. You can find the TP Toolkit, which is a plugin for Cinema 4D, on ThinkParticle.com and learn more about it there, and you can find the rest of the series there too. So in this video, we're going to talk about the TP Dynamics object. So this is our normal dynamics object. We have a lot of other dynamics objects that we'll talk about or have talked about, but this is the general one for general use dynamics. If there's something you don't know how to find and you need to find it, go ahead and add this and see if it's in there. So you have the dynamics object, and in this case we're going to have a simple emitter as well. So let's go ahead and just hit play and see what's going on here. So first of all, we have some particles that spin out and then they bounce. So they explode out, spin, and then with gravity they fall and hit this box and they bounce off of the box. It's a deflector. So let's go ahead and see how we set that up. And I think there's some variation with some turbulence as well. So this is a very interesting setup. It's great for MoGraph, things like that, these sort of explosions. In fact, this is a kind of similar setup that we used to the TP Toolkit banner image up here, which you can check out. So we had some particles that shot out and spun along the x-axis. Yeah, so we'll show you how to make that. So first of all, there's a lot of tabs with a lot of settings. And the first one is the most important one. It's a single setting on the General tab. This is how to set the particle group. So if you don't know what a particle group is, it's like a last name. And anybody with the same last name has to follow the same instructions. So you're going to have the Andersons and the Scotts and the Richards and the Jordans. And anybody that's a Richard needs to, or the Richards family needs to all have gravity applied. But the Scotts, they don't like gravity, and they got lucky. They actually don't have to apply. They don't have to follow gravity, but they do have to follow motion inheritance. And then the Jordans, they have deflectors. They hit those deflectors and bounce off of them. So that's their defined nature that we set up with these algorithms, and it's really easy for us to set up. It's just our settings. The computer takes care of the work, but we say this particle group right here, the TP Toolkit, is going to have all of these settings applied. So we're going to start at mass and go through, and I'm going to talk about what's constant between all of them first. This checkbox, enabled or disabled. So if you have it checked, this setting will be applied to your particle. So if you have a particle that already has size applied to it, this will overwrite those settings if you don't uncheck it. So go ahead and uncheck it if you need to. So in this case, we have our particles that shoot out, spin, and fall down. So there's a lot of variation in this though. And we have our mass applied. So a particle, so basic physics, every object has mass. And I'm not going to explain how physics work right now, but this is where you apply that mass to that particle. And you can give variation to mass and apply it over life too. And that will allow you to give some variety to the rest of the settings, which I'll talk about in a bit. So in this case, we're applying a mass of 1 with 100% variety, and we can change that to apply over the age too. So when a particle gets older, it can have a mass of 0, and when it's young, it can have a full 1, a mass of 1 with the overage gradient. The age gradient, like our other settings, we have a spline controlling them. And that's something I had to custom design for a lot of our settings to give that variation that we were looking for, or I guess that level of control we were looking for. But Cinema 4D natively does age and or mass and size gradients, so that's something that we applied, or not applied, we threw in from the very beginning with these age gradients. So that is a different way to apply it. So if you want to mimic that age gradient from white to black, it looks like this. It starts with a value of 1 and it goes down to black. Okay, and that is how that works. So there you go. And that is the exact same thing with size. And instead of having the mass the particle now inherits a size, and that has that variety. So we're going to add a cloner and a sphere in this case. We're going to change it up and get really exciting here, folks. All right, we're going to go ahead and have each object have its particle scale applied to it. So when we use a cloner object and add the particle group to what we're cloning to, and then take that particle scale and set it to 100%, then we're going to be able to use that scale that we set in here, or that size. So if we set that size to 100, those spheres are going to be their normal size. But if we set it to 10, they're going to be 10% that scale, okay? Now if we set that to 50% variation as well, some of them are going to be bigger than others, and some are going to be smaller. It will always have 10 be the biggest size, and then it will go down to 50% of that value, which is 5 as the smallest size, and it will range in between. Then we can also add an overage gradient, so as they get older, they get smaller and disappear, which in some cases is great for a particle animation where a particle flies into the scene and it just grows in, and it doesn't just appear out of nowhere, really harsh and jagged, which is never really very visually pleasing. So an age gradient like that is very practical. So that is how the age gradient works for size, and how size works. Okay. Next, we have some friction. This is like air density, or traction, I guess. It's going to slow down your particles. So if we just turn that off, you'll notice our particles are going to fly out much further, but if we apply friction, they're going to be more restricted, and it's going to slow them down. It's going to take their velocities, and it's going to say, all right, I need you to slow down a lot more than that, okay? And then you have your spin friction, so if a particle is spinning, and then because, you have your position of a particle, and then you also have the spin of each particle. And those are things that are applied with dynamics and other objects that we have in the TP Toolkit, and also in Espresso and things like that. So here I told you that we were going to look at how the mass will apply to other settings. In friction, we wanted to give it a variety so that it would not just be a friction of 4 applied to every value. We wanted it to spread out more than that. So in this case, it actually goes between 2 and 4 because the mass dependence. So it depends on the mass. If the mass is 0, it will apply differently than a mass of 1. And in this case, because the mass is set with 100% variety from 0 to 1, each particle has a different mass. Some particles have a mass of 0.2, some have a 0.8 mass, some have a 1. And this allows us to take anywhere between the value of 2 and 4 because we are using 50% of the value of 4 to add variation. So each particle will have a friction anywhere between 2 and 4. And then also that has the same thing with size dependence. Some particles are going to have a variety of size. So we could set the friction to have a size dependence. So some particles are going to have a different size. I already talked about that. So again, that makes it look different. So, and then we can have that set over age. So the older a particle is, in this case, the more friction will be applied. So it has about half the friction it would normally have at the end of its life applied to it at the beginning right now. We can set it to have no friction at the beginning of its life, and it will span out much quicker. And then it will slow down as it gets older. Or we can apply more friction at the beginning, and it'll just focus on spinning and falling. So we'll leave that as is. Next, John Mayer, gravity. Always trying to bring me down. So we have 2 different types of gravity, and we have our planar gravity, which if we go ahead and watch these particles, they all fall at some point. Like up here, they'll start to come down. They're spinning along an axis, and then which is kind of a vortex look. And as you can see, they have this velocity applied, and as they come up, they'll slow down because of the friction, and because of the motion inheritance and the gravity. All of these are taking that explosion of a particle moving out like this, and then changing where it goes. So gravity is set to 150 right now, and it'll fall down. And then you also have your decay value, which is a fall off. And then you have your mass dependence. So this again is taking the mass and it's giving that variety from the mass and applying that variety to gravity. It's a great way to give variation to your gravity, so nothing is entirely uniform. Next, you have your overparticle age. So the particles can just fly out, and then when they get older, they'll have gravity start to apply, and then they'll start to fall, which is kind of cool up here. And it's an effect I like, but I prefer the original effect that we had. Now we have wind as well. Oh, actually, you know what? We need to talk about spherical. So gravity can be planar, so everything will fall down or to the x-axis, wherever you point it to. Actually, we do need to focus on that really quick. The planar, we have our TP gravity object, and if we rotate that around, you can actually see. Oops, we duplicated it. Okay, so there's two objects right here. Okay, and it's because it is currently set to planar. There we go. Okay, so we have our gravity object. This is a square with an arrow that points the direction the gravity is going to pull. So if we set it to that direction, which is the default, which is just 0, or not 0, just down on the negative y-axis, then the particles are going to fall in that direction. But if we set it to, say, point in the negative x-axis, all the particles are going to move in that direction with a gravitational pull. It's a little different than wind. So now we're going to talk about spherical gravity. It's more like a black hole. Okay? It's like that person that just sucks all the energy out of you. And they pull you in. Actually, that's more like an attractor. So the way it works is these particles will fly out and the gravity will apply and the particles will all come back into that center frame. Okay? That is spherical gravity. So if you find that the attractor object in the TP Toolkit isn't really cutting it for your needs, you can add the dynamics object as a replacement to the attractor and use the gravity spherical setting to do more velocity sculpting and use mass gradients and variation, and then use overparticle age variation to really get that fine-tuned control. Next is wind. Wind is going to push our particles in a single axis, like such. It's a blustery day for Winnie the Pooh. And we can add variation to that as well. And then we have this wonderful thing that I always love. It's called turbulence. It's going to give us this variation of motion. And we can go ahead and move our particles around with these things. So, our wind is going to move the particles in one direction, but not like a boy band. And then we have our decay as well, kind of like our gravity. So wind is really actually the same thing as gravity. But in this case, wind with spherical is going to go outward instead of inward. Now you can use negative values, but it's not... Ooh, that actually looks like an atomic simulation, like that little Jimmy Neutron logo. Never done that before. Using the spherical setting will allow you to push the particles out on wind and in on gravity. And the x-axis that they move, actually they move across the z-axis with the TP wind, but we can make a move across the x-axis by rotating the TP wind object, which is under the dynamics tab right here. So, and for some reason, they're not moving the right way. And that's actually because of the motion inheritance, I think. So, yeah. So we'll go ahead and set that back. Okay. So we have over parent age. So the particles can be born and they'll spin out, and then all of a sudden they get older and realize, I'm going to follow the crowd, which isn't something they should do. But the wind is going to pick them up and take them with them over particle age. So as they get older, or at the beginning of their age, we can set that with that curve. They'll start to fly out, and then they'll be like, okay, I'm going to come back and do the right thing. So there you go. They start to inherit the motion inheritance, which gives you this really interesting look right here. Actually, I really like that. It's kind of like this crazy hairdo sticking out of this guy's head. Yeah. Anyways. All right. So that is how the age gradient applies. And next we're going to add some turbulence. So again, as you saw, this is like having wind but in random directions. And you can change that random direction scale by changing the structure size. So a structure of 1200 is going to give you a broader, more general flow for all of the particles to follow. But if you set it to, say, 12, almost every particle is going to have a very different direction to follow. So if you set it to 12,000, almost every particle is going to follow the same direction. Actually, right now it's not. I don't know why. We'll set that even higher. And turn the turbulence value up. For some reason that wasn't really working. It normally does. It's a weird little bug in this case. Take my word, it does work. If it doesn't work for you, let me know though, and we'll fix it. So you get this really cool spiral effect in this case with the bouncing off of that object. So that's one reason to use turbulence. You can get these really cool variations like this. And because we have the frequency set to 0, we found that nice little pocket right there in the world space where there's this nice little turbulent vortex. Very cool. And these particles all move in that sort of direction. So it's great for designing very dynamic procedural looks. So we're going to set that back down to our native settings that we had it at. And we'll just, oops, that's not what I wanted, reset to default. And you can apply, again, turbulence over the age of a particle. So we'll add a lot of turbulence. Okay, a lot of turbulence. And then it will apply over age, but when it gets older, it's going to get really intense, but when it's younger, it'll stay pretty small in its speeds. So as you can see, the particles are moving, and then all of a sudden, they're going to start getting really crazy over here. If you watch, they'll move so fast you can hardly see them. So that is how the over age gradient works for turbulence, just like the others. Okay, the next one, almost there, almost to the last one, is motion inheritance. So how are these particles spinning? That is a null object. And if we turn off the emission of particles and select our null object here, you can see a null object that I animated to constantly spin. So for the span of 3 seconds, it will spin twice. And then I set it to continue afterwards with the keyframes. So one great way to do that is to open up your timeline, and it starts like this. Here's a rotation value of 0 and 720, okay? And that looks like this in the graph. And normally, that last key is just going to be off after. But you can set it to continue after, and it will go on for as long as you want. Actually, probably much longer than that. It goes on forever. So that object spins, and the particles will inherit the motion of that object. In this case, they'll spin around that center axis. So let's go ahead and see how we set that up. So with a value, actually we need to set that object in there. So we can drag that in. Then with an inheritance value of 100%, you can have each particle inherit that speed, that spin value, 100%, and then we have a variation of 50%, so each particle will have a difference of variation. So if we set it all to 100%, it will look a lot different than, say, that 50% variation. With a 50% variation, it's actually going to let the particles move outward more. Then you have your rotation inheritance and your velocity or variation on the rotation. And then there's a direction variation. So if we set that to, say, 35, it will add a lot of variation to the direction of the particles. And it can be useful, and sometimes it's not. So sometimes it won't help you get the desired effect. But that's a variation in the direction it goes. It moves. And the rotation inheritance, again, the particles right now are moving in a vortex. So that's actually a position control, right? So if we wanted to inherit the rotation, that would just move the rotation, but the particles don't actually move. So that's why we're inheriting just the position for the rotating. So if you want to do a vortex look, and inherit the position values, don't inherit the rotation. I mean, you can, but, you know, they're not going to get you the look you're looking for. So And then we have relative T1 and T2. And I probably should have explained that in the actual name. So in a future update, we'll rename that. But this is basically saying this is the lifespan of the particle. This is the birth and the death of our particle. And this is relative to that particle. And this is where this will apply. So it's kind of like having this spline right here. This is the beginning. This is T1. And this is the end, T2. This is time 1 and time 2. So this is 100% of the life. But say we only want it to apply to half the life. We only want the particles to spin for 50% of their life. And after that, whatever velocity they inherited, they're done. You're going to just keep that and then just move on with your life. Or say you want to inherit 5% of the lifespan. The particles will spin for about 5% of their life. Actually, exactly 5% of their life. Because that's the nice thing about computers. They are exactly obedient. So the particles can, say, move and be inherited. They can inherit the speed based off of the commands that you give them. In this case, they will not inherit any speed values until they have had 50% of their life. Okay? That's a very hard number, very constant, very solid look, which is great if you're looking for those jagged edges. But if you want it to inherit that over time and have kind of an easy ease into it, you're going to want to use the overparent age. So it will ease in and have a softer control over it. And it will take in those particles and inherit the velocity. In this case, it's spinning an object, but it can also be applied to a motion of an object. So say you're emitting particles along with a sphere, and that sphere moves in and then stops. Well, the particles don't stop. I mean, they would fly off of it, right? That's velocity inheritance. That's what you can use the inheritance for. So the last thing we're going to talk about is something we've talked about a few times earlier with different objects that use deflectors. So if you've already seen those, you know how this works. Otherwise, go ahead and check this out. So we have this cube right here, and we're using a display node to view it as lines, as a wireframe. And that gives us this cube that we can see that basically says, all right, when a particle comes to my face right here, it's going to bounce off of it. Okay, you can see right here these particles are bouncing off the face. So it's actually a really great bounce right there. Nike. Just kidding. So you have the ability to offset that with the particle size travel. Say you want to have the particles bounce. And because the size variation is applied, those particles are going to fly off pretty quickly on some of them. So as you can see, some of those particles actually get closer to bouncing than others do. None of them hit the surface though, because we set that particle size travel. If we use a user-defined travel, they will all hit at 15 units from that surface. Okay? They haven't touched the surface. But if we set a variation of 100%, they will touch the surface or not, depending on which particle it is. Some will bounce 15 units away, some will bounce 0 away. So that's just that variation that we add to it to go between 0 and or between whatever value and we set and the variation. So 50% of a variation of 15 will be 7.5. So it'll go between 7.5 and 15. So just more math for you. Collision type. So say we want to only collide with the backside. We love backcountry skiing, so we're going to go with the backside. So now the particles are going in and bouncing on the inside of the cube only. So every polygon has a normal. Okay. If we select our faces and make sure we have normals checked and then we uncheck wireframe, and we select all of these, deflector cube. Okay, so this face right here has a normal. This is the front side. If we reverse the normals, that's the back side. And the back side is the dark side of the force. So if you apply it only to the back side, that's going to hit the inside of this cube only. Okay. You can also apply it to both sides. So sometimes you're going to have particles go through because they're just moving too fast and the computer can't calculate it. And they will go through the object, and having the backside as well will be a nice catch and release, sort of. Or, okay, not a catch. It's kind of a backup plan sometimes when the computer's not simulating properly because the simulation is just too freaking awesome, just too intense. So you have your bounce, and these are bouncing 100%. Say 500%, the particles are going to hit and inherit the velocity they originally had and multiply that times 5. So it will be 500 times, or 500% of the original velocity that they hit that polygon with. And then we'll talk about velocity inheritance, and then we'll show you where to find the rest of these because it's complicated, and we've already talked for very long. So let's go ahead actually and just find the rest of those really quick. Under the Help menu, you go to Reference, Cinema 4D, Visualize and Broadcast, and Studio. Okay, then you go to Thinking Particles, Nodes, TP Dynamic Group, P Deflector. You can also type P Deflector, and that will help you find that. And then you go to the P Deflector, and then you go to the Parameters, and that is where you can find these. And it's between Surface and Chaos, and that will help you understand how those settings work. Okay, so go ahead and read up on that, and that will teach you how to work with those. And then the velocity inheritance basically takes that cube right there and say it moves from here to here over its lifespan. So we're actually going to do that. It's going to be really exciting. We're actually going to start animating instead of just letting the computer do it for us. This is a first. All right, so it's actually not a first. We're going to go to frame 80 and pull it up. So the cube is going to move, and these particles are going to hit it, and they're going to inherit that velocity. So in this case, we're going to turn the gravity way up, okay? Particles are going to come down, and the bounce isn't, as you will see in a moment, the bounce is not going to make the particles move once it stops moving. The particles are just going to sit there, which doesn't make any sense, right? You need some velocity inheritance. You need to inherit the velocity of that object 100%, and then they can bounce, okay? And that will be more accurate. So if we set that velocity inheritance to 500%, it will move 5 times as fast as that object moves, plus the bounce. So some exciting stuff. It's like this epic trampoline. So that is how the TP Dynamics object works. So we went over each individual tab, talking about each setting, and it took a while, but we got through it, so thank you for sitting with me. And thank you for watching this video, and you can find the TP Toolkit and all of its wondrous glory on thinkparticle.com, and you can find the rest of the series, the visual documentation series there as well. And I'm Sam Wilker, and I'll see you guys later. Thanks for watching.